All right, so last time we finished at defining with combination coefficients, right? And there was an example, so example was so select three people, three persons from 30. And so if you select 3 persons from 30, and it doesn't matter in which order you select these 3 persons. And the answer was that it's division in 2 groups: those who belongs to the group of 3 persons, those who do not belong. So the answer will be, in principle, multinomial coefficient with groups of 3 and 27. So in principle, the answer would be 30, 3, 27. And so, but for this coefficient, there is a special name, which is kind of this 30 and 3, just without mentioning this 27. Right? And so this is a very common problem. So select some subset of people, right? So kind of a subset of object. And the answer is given by this thing. So so it's in principle, it's a theorem, but this is example perfectly illustrates this theorem. So theorem says that the number of ways to select a set of k elements out of maybe kind of here should be a subset of k elements. Maybe here a subset. A subset of k elements out of set of n elements is nk. And this is the same thing as C and K, so just different notation. Right? And same thing as n factorial divided by k factorial divided by n minus k factorial. So it is this coefficient, it is called number of combinations of k out of n. And so this is the most popular coefficient, or, well, so you know that it is also called a binomial coefficient. And so this is old name from combinatorics, and binomial coefficient is also old names, but I think binomial coefficient now is more popular than number of combinations. And then binomial coefficient is also kind of, because it's like multinomial coefficient, so it's also called binomial coefficient. And it's called it this way just because if you use a binomial formula, so if you look at binomial formula, and binomial formula just says how to expand this expression x plus y to the power of n, and it will give you, you know, that this is xn, and after that it will be plus, and if you kind of calculate, if you just really expand, it will be x to the power of n minus 1 and y, but y you can choose, so you have x plus y, and so on, x plus y. And so here's n times. You did it x times, and you can, if you kind of, you have x to the power of n minus 1, and after that you'll need to choose one of the, so you need to just choose one bracket, and from this bracket choose y. From all other brackets you choose x. Right? So it will be n 1 x to the power of n minus 1 y. Plus, if you need a next coefficient, you need to choose two brackets from which you choose y, and from all other brackets you choose x. And so it will be, here will be, so here's n minus 1, here's n2, x n minus 1, x minus 2, y to the power of 2. Right? And you continue. So you see that here's the coefficient with binomial coefficient. So n choose 1, which is equal to n. Right? So n choose 2, which is equal to n multiplied by n minus 1 divided by 2, and so on. So, and finally you will get to the last, which will be n minus, first before last, n minus 1 to the power x, and here is n minus 1, so x to the power of 1. And after that, y to the power of n minus 1, and the last will be y to the power of n. So in principle, you can also think about that here's the coefficient 1, but you can, in principle, you can write here n0, right? Because n0 by convention is equal to 1. So in principle, you could also here write n0. And because of this formula, and so this x plus y to the power of n is equal to this thing, so which you can also write this thing compactly. You can write it this way. So it's k from 0. Right? So you can kind of, here will be 0 coefficient to n. So, and this one you also n out of n, so also 1. So, and here you'll write n k x to the power of n minus k, right, y to the power of k. Or you can switch kind of. So the coefficient, this coefficient are symmetric, right? So we wrote down that n out of 1 out of n is also equal to n minus 1 out of n. And so everything symmetric. So in principle, you can write here x to the power of k and y to the power of n minus k. Doesn't matter. And so this is the reason why it's called a binomial coefficient. Right. Okay, so now let's stop off with combinatorics and look a little bit on the problems in the probability, and in particular on how these things can be used to calculate some probabilities. Okay. So since this was used initially for analyzing various games of chance, so there are many examples which are kind of still uses examples from the world of dice. Dice is from the world of card games, and so just as a reminder, just standard deck of cards. So it has a 52 cards, and so probably most people know it, but just kind of let us fix it. So 4 suits, and so which is a kind of so which are the suits? So hearts, and spades. So whichever, just remind me, because I know it very well in Russian, but I don't know what it is. I don't remember so well in English. Diamonds and clubs. All right. Okay, so diamonds. Diamonds. And clubs. And so now, so 4 suits, and so every suit have 13 cards, right? So 13 cards in each suit. And then by convention, they ordered kind of like 2, 3, then 10, then Jack, then Dame and King, and for an Ace. Right? So okay, and so 13 cards. Right? So and mostly we just need kind of these two numbers, 13 and 4. Right? And right. All right, so here's one example of a question. So again, so this is just kind of, well, just questions to illustrate the problem. Strangely enough, kind of these methods are really kind of useful in theoretical developments. When you build a model, in many cases you really use this kind of to calculate the probabilities. But it's easier to illustrate using these examples. So example. So now here we are looking at the example of having a full house. Right? So what is a full house? So full house, so terminology from poker. Right? So it's 3 cards. Of 1 rank. So okay, and hand, kind of a regular hand, so it depends on the game, but kind of, so in poker, a hand, so it's the cards which are given to a kind of a player, and it has a five cards, so in poker. And so you have a, if I'm not mistaken, so kind of, right, so kind of, so you have a full house if you have 3 cards of 1 suit and 2 cards of another suit. And so this is kind of have some value. So so we kind of just interested in the question, what's the probability that we'll, if kind of after we open our cards, we will see this particular combination. So what's the probability of this particular hand? Clubs, diamonds, yeah. There's 3 cards of 1 rank, not suit. Let me see. Yeah, you are right. Yeah, sorry. So 3 cards of 1 rank, yeah. So you kind of, you see my skill in poker not very great. And 2 cards of another rank. And so rank, so it in particular, well, kind of, so what would be example? So if you have a 3 jacks, and as far as I understand, say 10 and 10, then this is a full house, right? And so we want to figure out what's the probability to get one of this combination of these combinations. So now how we can reason about this. And so it's not a straightforward application of this rules, but it's not very difficult here. So first of all, let us think about kind of, so it's a probability. So it's number of combinations to get this particular hand. So the number of ways that you will get this hand, and divided by the total number of possible combination, total number of hands. Right? So the total number of hands, and so this is easiest. So you have 5 cards in a hand, and the total number of cards is 52. So this is a choice of 5 cards out of 52. Right? So this is a possible number of different hands. Right? And the order of the cards, of course, doesn't matter in the hand. So the total number of hands yes. Okay, so here we use it 52, 5 out of 52. And so now here it's kind of possible to calculate it. So in principle, so it's calculatable and it's equal. So by our usual rule, it would be kind of either kind of if you don't have a software, so the easiest would be calculate 52 times 51 times 50. So 5 times here times 49 times 48. Right? So 5 of this divided by 5 times 4 times 3 times 2 times 1. So which would give you like 2, 5, 9, 8, 9, 6, 0. 8, 9, 6, 0. Right. So which is approximately 2.6 to the power of 10 to the power of 6. So it's not so very large number of combinations. So kind of, so pretty, it's not very large, several millions of combinations. So if you look at some other games like a bridge, you would find much larger number of combinations. And so now this is something kind of which will be numerator of ours. So our probability would be this number 52 divided by 5, and here we'll need to figure out number of possible full houses, hands which are full houses. So number of full. And then here is also more or less clear. So if I'll tell you what's the ranks, and so then it's clear. Then in this case, so if I'll tell that the ranks should be this jack and 10, then so just kind of tell you this should be this is jack and 10. Then the number of ways to choose a triple of jacks, well, there are 4 jacks, right, in the deck. So the number of choose a triple is equal to 3 out of 4. And so now here will be have 52, 5, and so 3 out of 4 for this specific rank, and 2 out of 4 for this specific rank. And so in this case, well, if you knew that it's jack and 10, then you would kind of easily wrote that this is equal to 3 out of 4 and 2 out of 4. And so, but before kind of you can do it, you need to choose this. You'll need to choose what is this specific ranks. And in this particular case, it actually matters whether kind of it's, so whether it's triple or, so if we, so kind of it's actually matter which is is a part of a triple and which is a part of a tuple, right? Of double kind of. So kind of when we choose, so we can just choose them. So how many ways to choose the part of a triple? So well, so we'll have how many ranks? 13 ranks, right? So we choose one of them and say this will be our triple, right? So here's the 13, and after that, kind of after we did it, we also have 12 possible choices for another rank. Okay? So multiply by 12. And so now here's so why I thought it's kind of different, because it would be definition of full house maybe would be something different, and kind of two cards of one and two cards of another rank, when maybe kind of after that you would need to divide it by 2, because it kind of, well, doesn't matter which kind of you choose first and which, but here there is a clear distinction between triple and double. This is a subtlety, but kind of, so just you don't need to divide it by 2 here. So essentially, because kind of a choice of a triple is different from a choice of a couple of the cards. And this is kind of the answer. So 13 times 12, choice of the ranks, and after that, once the ranks are fixed, you choose what specific cards you choose from the 4 cards of one rank and 4 cards of the other rank. So this is 3 out of 4, this is your triple, and 2 out of 4, this is your couple of the cards. So, well, and this is, well, in this particular case, it's very easy to calculate, because here's 4 and 3 and 4 and 2, it's easy to calculate things. So it will be 13 multiplied by 12. So 3 out of 4, by symmetry, it's the same as 1 out of the 4, so it's 4. Right? Multiplied by 4, and 2 out of 4 is 4 times 3 divided by 2 times 1. So maybe we can write it, but it's kind of, so 4 times 3 divided by 2 times 1, but it's kind of 6. Right? Then after that, you divide by this number here. Right? 52, 5 out of 52. And so this is equal to, so let me see, what is this? If you do this, then you'll find out that, okay, so this is equal to, this thing is equal to 3744 divided by this 2, 5, 9, 8, 9, 60. And it turns out that this is equal to 0.00014. So if you kind of don't want to see so many zeros, you'll just write that this is equal to 0.14%. So pretty small probability. So this is one possible calculation. So now let us calculate another probability of some other hand of cards. Okay, let me remove it. So this was full house, and another one, so that we'll look at is so a flush, right? So kind of, so there are different types of flushes. Kind of one of them is a royal flush, which is kind of impossible to beat. But we use the regular flush. It just means that by definition here, it's just 5 cards of the same suit, right? And so it's not a straight flush. So straight flushes would be that these 5 cards have a kind of something like a 2, 3, 4, 5. So kind of going without gaps, kind of. But this is just a simple flush. And we're just interested to figure out what's the probability. So it's 5 cards of the same suit. Right, and we are just interested to know what's the probability probability of a flush. Not some specific, but just this is kind of can be anything. So if you look at the table, kind of how this hence valued, then you'll see that flush is it's as far as I understand, it's a smaller it have a smaller value than full house, right? So at least what I see here. And so it's smaller value of a hand means that it's probably more probable, right? So because it's natural to think about that more valuable hands will come to you more with less probability, less frequently. Right? So we trying to justify this intuition, right? So all justify this rule that flush is less valuable than just arbitrary flush, not a straight flush, not a row flush, just arbitrary flush is less valuable than full house. So for this, we'll need to calculate this probability. And we know that in this case, so the denominator would be the same, right? So it's the number of hands, 52 out of 5. Now, and here's also easy thing to analyze. So it's 5 cards of the same suit, right? So suit has 13 cards. So you will have that here, you have a 5 out 13. Right? But you'll also need to specify what's particular suit. Right? And the number of choices for a suit is 4. So this should be the answer. Right? So let me see if it agrees with what is written here. Yeah. And so now you calculate it. So this is already calculated, and 13 out of 5. Well, so 13 times 12. So this is 13 times 12 times 11 times 10 times 9. 13, 12, 11, 9, 9. Well. And divided by 5 times 4 times 3 times 2 times 1. And so if you calculate this thing, this gives you, okay, so this whole denominator is 5148 and divided by this number. Right, but it's already here. So already here you see that this number 5148, the number of possible flushes, is greater than number of possible full houses, right? And denominator is the same. So we'll see already that the probability of this thing is larger. And then if you calculate this thing exactly, right, then you'll see that this is approximately equal to 0.2%. So here's 5,000 approximately, and here's approximately, well, if you round up, then it will 4,000. So they are comparable, but this is more likely. It's more likely that you will get a flush than a full house, and this justifies that this is less valuable combination of cards. And this is you can you can calculate all possible combinations in poker. So there are many of them. Well, it becomes a little bit more difficult, right? So this is probably the easiest why I choose them. And so for it would be more difficult to calculate the probability of a stray flush and so on. Right? But this is a very good source of problems of this kind. All right. So okay. So. So let me see question. Is that the probability of specifically getting or any full house, not with jacks and tens. Jacks and tens just was an example of specific full house, and the probability of this full house would be in this case, you would need this 13 times 12. Right? So because the only thing that I have not said to you about this jack, 10 and 10. I have not said which specific jack hearts, jack or something like that. So if I just wanted to figure out what's the probability of this full house, jack, and 10, 10, then it would be this thing, right? Without 13 multiplied by 12. Right. So where can you explain when you got 4 from? Yeah, that's right. The answer is right. So 4 is 4 suits. And so to specify a flush, you'll need to you'll need to specify what suit, kind of, right? So hearts or kind of diamonds, right? So you can flush in hearts, you can have a flush in diamonds, and so on. All right, so now maybe another example. So, but not in this. This is kind of, well, this is very nice example. So maybe kind of you kind of look at them in homework, maybe kind of not so much, because these are nice examples, but these are not kind of very kind of enlightening example. And so just like a puzzles, how to figure out these things. So another example, which is kind of important, but I think that it's used in many further developments, is something like a variation on an example that we used before, when we flipped, when we throw several coins and look how many heads. And so now kind of let us look at more generally at these situations. And so here's example. And so throw say 5 coins. Let's say 5 coins. And so for this specific, so previously we looked at 3 coins and said what's the probability that there are more than 2 heads or 2 or more heads. So let us here just say kind of exactly say 3 heads. So what is the probability? What is the probability to get exactly 3 heads? Right. So in this case, it's the same thing. So first of all, we need to figure out how many possible results. So how many possible sequences of heads. Not even the sequences. Yeah, maybe kind of just how many of possible sequences. Yeah, so kind of, so let us look at 5 coins. So one possibility would be head, 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 and so on. No, not so on. So head, 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 head. Yeah, so maybe I'll choose too many coins, but okay. So another would be something like head, 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 tail, and so on. And the final would be tail, 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 tail. And we kind of already have a recipe how to do it, right? So we know that for the first coin, we have 2 possible outcomes. For the second coin, we also have 2 possible outcomes. So the number of all possible sequences here, so number of possible sequences is 2 times 2 times 2 times 2 times 2, 5 times, right? So because 5 coins. So, well, which would be easier to write as 2 to the power of 5. Well, in principle, you can calculate it with this is 32. So now, the second thing to figure out is the total number of possible outcomes that you can get. And then now the next question is, so we'll look at this all these outcomes and see how many of them. So there are 32 of them, which is too much to do, but how many of them have exactly 3 heads? And this becomes difficult because if you list it, it's a huge number. So maybe we'll just say kind of, let us approach this. So we have some heads, some kind of results. So this is the results, and we kind of trying to figure out how many of these sequences have 3 heads. So just kind of choose places for this 3 coins which have a head, and say, so all right, so this will have a head, this will have a head, this will have a head, all other have a tail, right? And so now we kind of coming back to our problem about how many ways to choose the places of these coins which have heads. All other will have tail. So you can think about this as a committee kind of, right? So this is kind of, you have a committee of 5 coins, and so, and we select, well, maybe kind of, it's not a good analogy kind of, but kind of you have 5 coins and you choose what's the 5 coins that you have that have a head in them, right? And all other coins will have a tail, right? So maybe kind of, so 5 is too large number, so maybe kind of illustrate it with an example with smaller number of coins, like the 3 that we had before. And so similar situation with 3 coins and 2 heads. So what I'm aiming here is to say that the number of possible sequences that have 3 heads will be 3 out of 5. So in this case, so similar situation is 3 coins. In which case this is good because I can list them, right? So it will have this head, 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 tail, head, tail, head, head, tail, tail, then tail, head, head, then tail, head, tail, 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 head, and tail, 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 right? So all of them are different, right? Seems to be, right? Yeah, so this is the first tail, and after that, so more or less, yeah, so 8 of them, right? So now, how many of them have 2 heads? So this one, then this one, then this one, and that's it, right? Right, and so you can think about it kind of so that I have here empty spaces, and I select, so I need to place 3 heads in these boxes, right? So I place it here and here, and the remaining I put a tail here. So this corresponds to one of these combinations, head, tail, head, right? And so for every choice of boxes in which I put heads, well, there is a combination here, right? And this is kind of this is a bijection. It's kind of, you kind of have a one-to-one fashion, right? So if I'll say kind of, here's another, this is my different choice. This is head, I put heads here, head and head here. So I choose these 2 boxes and put head here and tail here, right? So it should also correspond to something here. It corresponds to A. And so it more or less should convince you that there is a kind of, so this is kind of how I choose the boxes in which I put heads, right? And so how I group the these coins, which I identify the boxes in which to put heads and in which to put tails, right? So this is a group, I need to choose 2 coins and say this will be this will be our heads, right? In my sequence, right? And well, kind of every choice of these coins corresponds to some combination. All kind of choices here. So if I choose head, tail, if I choose these 2 coins and say heads in them and tail in another, it will be different combination. And I choose these choose 2 coins and say put heads in this and tail in another one. So first of all, every choice of mine corresponds to a valid sequence. And second one, if I choose different make a different choices, it will correspond to different sequences here. And so it's this is kind of my way to count. So this is how I will count this number of these possible sequences that have 2 heads. And so in this particular, so now the problem is choose 2 coins out of 3. This will be coins with the heads. So in this case, it's 3 coins and I choose 2 of them. So the coefficient 2 out of 3. So 2 out of 3 ways to choose coins that will have head. Right? And once I made this choice, it corresponds to one of these sequences, possible sequence. So this number 2 out of 3 corresponds to the number of sequences with exactly 2 heads. And so this is in this simple example, it's more or less clear. Right? So this is so just I found a way how to count this. So that kind of, and the nice way about this way of counting the sequences that have exactly 2 heads is that it can apply to any number of coins and now any number of heads. So here it's applied to 5 coins and 3 heads. If I have a very general problem, if I have a problem that so so let me finish the previous problem, because we asked not about the kind of just the ways to get, but we ask about the probability, right? And the probability, so in that particular example would be 5 over 3. So this is the number of sequences that have exactly 3 heads. The number of sequences of the coins which have exactly 3 heads divided by the total number, and we calculated the total number was 2 to the power of 5. Right? So, and in this particular case, it's easy to calculate. So 5 out of 3, and it's the same thing as 2 out of 5 divided by 2 to the power of 5. Right? So this is 2 out of 5, 5 times 4 divided by 2. So it's equal to 10. Right? So we already kind of seen it before. So 10 divided by 32. So, but in general, so more generally, so if we throw n coins and maybe here, right? So maybe here say fair coins, right? So we always here assume that all outcomes have the same probability. So if we throw n fair coins, then the probability to see k coins with heads and n minus k coins with tails. So it's generalization. So here was 5 free, here will be n k. So k, n choose k divided by, and here was 2 to the power of 5, so here will be 2 to the power of n. And then we will see later this probability. It will be useful in the later development. Why does the 3 go to 2? Here, top left, when is 5 over 3 over 2 to the power, here, okay, so 2 and 3, well, it's symmetry, right? So I did it because I did, well, kind of easy to calculate 2 out of 5 and 3 out of 5. Well, it's the same thing out of calculating, but I just was trying to explain why it's very easy to calculate this thing. So this is n, you have a identity nk is equal to n minus k. And it's because, well, if you write it, then the first one, n factorial, k factorial, n minus k factorial, right? And here's the same thing. So it's n factorial divided by n minus k factorial, right? K factorial, which is the same thing. So you just change these two things, right? So this is the definition. This is the definition of the first one. This is the definition of the second one, and you'll see. Well, so this is the same thing. Right? So, and why I kind of put it 5 over 2? Well, if you calculate this thing, so automatically I would calculate it 5 times 4 times 3 divided by 3 times 2 times 1, which is not so easy. And here would be just 5 times 4 divided by 2 times 1. Right, which is kind of, I can do in my hand, right? So it's 20 divided by 2. And here, well, it would be 20 times 3, so 60 divided by 6. So it would also possible to do, but kind of for laziness, usually kind of you choose something which is have a smaller thing here. Right. So this is one of these identities that relate. So as I said, that there are a lot of identities. So if you look at binomial coefficients somewhere on the web and kind of read the article, Wikipedia article about the binomial coefficient, it lists a huge number of identities. Right? So this is important coefficient. So many people kind of looked what's interesting can be said about this. And so, and we found kind of some, so I just right now, I don't remember kind of something really interesting kind of things which are related to these identities. All right. Okay, so now this was important example just because it kind of will be used in the future. And another example is less important, but it's kind of one other illustration how this thing can be applied. So it's this example says, so just one kind of example. So suppose that you have a group of people. So this is example, group of people. So 3 boys, so 4 boys and 3 girls. And 3 girls. And you usually you want to select a committee. So they select a committee at random. And so kind of everyone kind of drop a paper slip in a box, and after that we take this paper slip out of a box and kind of, well, you find out the committee. So how many numbers in the committee? So 4 numbers in a committee. 4 members. 4-member committee. randomly. And by randomly, I mean kind of, again, so kind of by randomly, you mean kind of either this procedure that I said, or just you list all possible committees, and after that, choose one of this committee. Okay? So just kind of all possibilities. Okay? So now the question is, what's the probability? What is the probability that this committee, it has 2 boys and 2 girls. So the similar problem is sometimes kind of you can get this problem is kind of if you analyze something like a selection of a jury, for example. And so in some cases, if you analyze selection of a jury, in this case, you might ask the question whether there was some kind of a discrimination, and you'll need to kind of figure out what's the probability of getting this particular outcome. Right, or something like similar. So this is a baby example of these problems. Right? So here, what's the probability that the committee of 4 members chosen totally randomly has 2 boys and 2 girls? And in this case, and so we use the fact that everything here is, every outcome is believed to be equal probable, and first of all ask and use this classical formula, number of possibilities, number of possible committees that have 2 boys and 2 girls divided by the total number of committees of the 4 members out of 7 people. Right? So this probability, so first one is how many committees we can choose. Just different committees, and we don't, committee doesn't have anything kind of, it's just a committee of 4 people. There is no kind of reason to believe that one of them is more important than another. Right, in this case, okay, so 4 members, 7 people, right? So here we'll have 7 and 4. This is the number of ways to choose any committee of 4 people out of 7 people. And then after that, we say, okay, so now we look at the number of possibilities that the committee have 2 boys and 2 girls. And so this is easy because it's kind of, so we just imagine that we'll do it separately. First of all, we choose the boys for the committee, and after that, we choose the girls for the committee. Right? So how many ways to choose 2 boys for a committee? So 2 out of 4. Right? And so how many ways to choose 2 girls for a committee? So 2 out of 3. Okay, so and then so that's it kind of. Right? So this is the answer. So if you can possibly calculate it, so it's easy to calculate it in this case. So 2 out of 4, it's 4 times 3 divided by 2, so it's 6. And 3 out of 2, well, 3 out of 2, it's the same as 3, 1. Right? So it's 3. And here's, okay, so this is a little bit more difficult, so you will need to calculate it, right? So probably the easiest would be kind of to say that this is equal to 3 out of 7 calculate it. But if you calculate it, you'll find that this is equal to 35. If I'm not mistaken, I didn't do a mistake here. 7 times 6 times 5. So it's easy kind of, so in principle kind of, if you don't have a software, this is very small numbers. So it's equal to 3 out of 7 by this identity. And so it's equal to 7 times 6 times 5 divided by 3 times 2. So this is cancel out, so it gets 35. And so this is approximately equal to what is 51.43. And so this is very kind of likely situation. Okay, so this is what we wanted to say about the combinatorial probability. Okay, so now we kind of switch from the combinatorial probability. So it's just kind of it's very nice to know it. In many calculations, this is kind of given kind of as a kind of standard piece kind of. So something which is easy, so usually very easy questions, and so usually calculations like that. And so, but it's not so important for the modern probability theory, just because in modern probability theory, usually, so this is a switch. You just don't assume that everything is equally probable, or you don't have a good assumption. What you are doing, you're collecting evidence from the experiment. Right? And after collecting the evidence from experiment, you are trying to do some conclusion about some other probabilities. Right? So you kind of trying to do inferences. So for example, if you collected some data, so from this data, you are trying to do some inferences about the probability of the parameters of the model. So if you kind of, or other way around. So you think about, so what's the parameters of the models? Let me calculate. So if the parameters of the models like that, what's the probability that I observe this particular set of the data? So you'll need to calculate it. So your assumption about the parameters, you need to kind of translate into the something about the data. Usually it is done to check your first assumptions, your initial assumptions. And so, and it's done by looking at the data and kind of comparing what's the probability kind of is, whether you observe something which is likely for a given model or something which is not likely for a given model. And this means that you not really want to calculate a simple probability. You want to calculate what's the probability if there is some assumption about the data. And so this is basically kind of why we kind of start to think about start to talk about something which is called conditional probability. So this is the next topic. This is more important than the combinatorial probability. So conditional. No. So probability of A. So probability of event A given that event B occurred. So maybe kind of this is a little bit abstract to talk about that it's used in science and statistics to calculate probabilities. But in this concrete example that we had before, what's the probability of the full house? You can see how it works. The conditional probability works in this way. So you can ask the question. So here we calculated what's the probability that you'll get a full house, right? Now, and this is kind of a probability that some player opposite you got a full house. Now you open your hand and you'll see what cards you have. And so you got some information about your cards. And so now what about the probability that the other player have a full house? Well, in this case, the probability will change because you can see that you have a kind of some set of the cards. So definitely he is not having this set of the cards. And so you will need to recalculate this probability. And this is the conditional probability, just a method how to do it. Right. All right, so let us look at the how it works. So it's a method to calculate the probability of one event under assumption that something else happened. And let us look at the this calculation, still assuming that all outcomes are equally probable. And so so assume, so here's a derivation. So it's not a definition, it's a kind of a motivation for the definition. So assume that all outcomes are equally probable, and n is the total number of outcomes. And so in this case, you'll have a probability of A is equal to number of outcomes in this event A divided by n. And so you can keep as an example this example with the full house hand. And so we calculated using this formula essentially. And so you also have a probability to B for B. And so this is, you can think about this as a probability of a full house hand of your partner, of the other player, and this is a probability of full house in your hand. So this would be B divided by n. Right now, so now we want to calculate what's the probability of A given that we observed B. So B was observed. So what is the probability of A? What is probability of A? Right, and in this case, it turns out that this is so all the word actually was destroyed. The previous word was destroyed. So we cannot use any formula like that, because right now we know something about the word, and the outcomes now, some outcomes now are totally impossible. Right? So it's impossible if you have a king of hearts. It's impossible for other players to have a king of hearts. So you'll need to rebuild the probability space. You need a different probability space. So in this case, so what's your probability space? Well, your probability space is the probability of all outcomes which agree with B. Right? So, and this means that it's B actually. So B consists of of some specific set of the outcomes. Now you know that B is realized. You don't know which specific outcome realized, but you know that some outcomes realized which is consistent with B, which some outcome realized which is consistent with your hand, with what you see in your hand. And so new probability space is this set B. So it's all outcomes which agrees with what you see. Right? So now, so number of elements in it equals to B. Right? So this is the number of all outcomes of possible deals of hands, deals of card deals, which is consistent with B. And so now, after that, we'll need to make another assumption that the fact that you observed your card kind of still all possible outcomes still kind of equally probable, right? So, right, if it's consistent what you see, all other outcomes are equally probable. Right? So this is a natural thing to do with natural assumptions. So you don't really know what other people have from looking at this. The only thing that you know that they cannot have something which is inconsistent from what you have. And so if you assume that all outcomes in this B are equally probable, then we can still write the formula like that. So this is P, so this probability A, and let us denote A given B because it's different from this thing. It's a new thing. So it's A when you observed B. Right? So it's equal to B here, all possible number, it's all possible number of outcomes consistent with B. And so now you'll need to figure out what is here. Right? And previously we had something like that. This was all outcomes, right? And there was something, this was A. Right, so this is the event A, and this was B. Right, so and you previously you said so with all possible number of outcomes in A, something. Right, so A, this thing. Right? So now you're saying how many now outcomes which are consistent with B and in A. Right? And this is, well, by definition, it's the outcomes which are both in B and in A. So this is outcomes which kind of say that the other player have a full house and you also have a full house. So it's both things are realized. And this is what kind of means that you looked at full house and you're thinking about kind of probability what he has, that the other player have a full house. So now you write that this is equal to A intersect B. So this is basically an intersect means that both should be realized. So this is the formula. So this is the formula if you kind of use the new probability space and assume that after you learn some information, the outcomes still are equally probable. So this is not some complicated information, which says, well, kind of you got this one and well, I'm not sure. In this example, it's difficult to understand to see how it could be other way, except that all kind of possible other hands are equally probable, and we cannot imagine kind of how it is possible. And so now, okay, so you can do this. So and after that, you still calculate, but it's useful to use something information. So maybe from our previous calculations, and so maybe it's kind of it would be useful if we could calculate it this in terms of the probabilities of A and probability of B that we calculated before that. And so let us, for this, we just do a simple thing. We're just saying that this is also equal to probability of A intersect B. Sorry, not probability. Number of elements in A and B, number of outcomes which are both in A and B, divided by B. So I repeat it and divided both numerator and denominator by n. And when divide by numerator and denominator by n, we kind of get a probability here. So B divided by n, so number of elements of B divided by n, it's probability of B. Right? And number of elements in A intersect B divided by n, well, we don't read it here, but it's probability of A intersect B. So it's equal, so probability of A and B divided by the probability of B. So if for some reason we already calculated probability of B, and we do calculated probability of a full house, for example, so we don't need to build a new kind of model. You just kind of can use this probability of B, which was previously calculated, but you also need to calculate probability of A intersect B, which might be difficult, maybe not, kind of. We will see later when sometimes you just assume that it's kind of not difficult to calculate this, just by assumption, kind of. And sometimes might be that you have not gained anything from this, but still kind of useful to use this. And so this is a derivation in the case when you have all outcomes equally probable. But after that, we say kind of, all right, so let us define the conditional probability in this way. So it means that in principle, we believe that something like that when you learn new information, it doesn't change the relative probability of outcomes. It still holds. But kind of from a mathematical point of view, we are saying, okay, so this is interpretation, and it's most kind of, we just define it like that. It's usually kind of, it's always true that something like that holds. And so that when you learn some new information about event, there is no some weird shift of the probabilities of outcomes. So, and also it is possible to see that it's kind of, you can derive this formula also if the probability of outcomes are not equally probable, just would be more complicated kind of argument. So if you kind of still need to some interpretation about the process of getting of information. If you do this assumption about getting of a process of getting information, do some reasonable assumption about them that it doesn't change relative probabilities of the outcomes, then this formula could also be derived without assumption that the original outcomes were equally probable. And so from our point of view, this will be definition. So this will be definition, which will kind of usually have a nice interpretation like that. So definition will say that probability of A given B just equal to this thing. Now, one bad thing here is, well, this definition, if the probability of B is not zero, it's not applicable. So suppose probability of B is greater than zero. Then you'll have this thing. So this is by definition. And so why kind of a bad thing? Because, well, kind of we are talking here about discrete probability spaces, and usually probability are positive. If the probability is equal to zero, then, well, it never could occur. Right? But if we talk about continuous probability spaces, we can ask a question. So the previous shot got, suppose that previous shot got in some specific point. What's the probability that, and something, right? So it might be that you are in the continuous probability spaces, it might be that you are interested in the conditional probabilities when the probability of B is zero. Right? But this is a more kind of difficult thing. And so it is possible to define the conditional probability even if the probability of B is zero, but it's a little bit more difficult. And so we will talk about it, not very difficult, just kind of change a little bit the definition, but it's kind of, all right, so that's basically it. So we are running over time, and next time, maybe we will do some example, right? So we repeat the definition. So this is just a motivation kind of this formula. We repeat the definition and start to doing this calculation with conditional probabilities. And kind of important thing to keep in mind that this is really kind of more important than combinatorial probability in the sense that everything kind of is built on the conditional probability. This conditional probability is the most important kind of thing in modern probability.